So good afternoon, everyone. Welcome to another edition of our Liftoff webinar series. Today, we're featuring our member AddUp Solutions, talking about additive manufacturing in the defense industry. So we're excited to hear from them. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs with LIFT here in Detroit. So hope everyone is remaining safe and well as we continue in this hybrid environment in many cases, but seems like we are getting closer and closer to getting back to normal, or at least whatever normal looks like going forward here. So thank you very much for taking the time to join us today. I have a few housekeeping items to go over before we really get started. This session is being recorded, so please put your phones or devices on mute. You should all be muted, but if you're not, please go ahead and do so. We will be posting this webinar, the recording of the webinar, on our website later on today at lift.technology, so stay tuned for that. We will be facilitating a Q&A session at the end of the presentation as well, so if you do have questions, please use the Q&A function on the Zoom bar that we're all very familiar with these days. So go ahead and type it in there anytime during the presentation, but we will save those questions and answers for later on. I also want to take a couple of minutes to talk a little bit about LIFT for those who may not know who we are and what we do. Are y'all seeing my screen?
I can see it, Joe.
Okay, great. So a little bit about LIFT, who we are and what we do. So LIFT is one of 16 National Manufacturing Innovation Institutes around the country. We are headquartered here in Detroit, and our mission is to drive American manufacturing into the future through technology and talent development. We believe that is the case for smarter manufacturing. We believe that on the manufacturing sector rests our national economic security and resiliency. And so that's why we have partners all over the country, members all over the country, because we know that the next industry or next area, the next region that tackles smarter manufacturing first is going to come out ahead. And we really want that to be the USA. So we are a Department of Defense sponsored manufacturing innovation institute. So that's why that is critical to us. So what do we mean by smarter manufacturing? Well, we really mean the connection between materials, processes, systems, and talent. So we look at manufacturing holistically. Our members look at manufacturing holistically. We want to make sure that we are not just being siloed, just looking at materials, because we need to know how those materials are going to be processed. We need to better predict how those materials will be processed. We need to know that they will be resilient and act the way they should in whatever system they're going to end up in. And we need to make sure that we have the talent that underlies all of those going forward. So we really run two programs out of LIFT: our technology program, Leading Innovations for Tomorrow, and our talent program, Learning Innovations for Tomorrow. Just put all that together, and you have LIFT. So, so what do we mean by Leading Innovations for Tomorrow, our technology program? Well, our technology program is you see the four pillars of technology that we have on the screen there. Everything from integrated computational materials engineering to agile and smarter manufacturing, advanced alloy and process development, and multi-material joining. I want to get a little bit deeper into those pillars here. You can see them on the screen now. I won't quiz you on those, but it shows the breadth and depth that we have, not only in-house here at LIFT in Detroit, but also across our ecosystem across the country. On the talent side of the equation, Learning Innovations for Tomorrow, it's still about innovation, still about new tools, new pathways, new venues. Kind of revolves around our Ignite Mastering Manufacturing curriculum. That is the earliest stage in which we operate. That is a 3-year program for high school students that is available now in 13 states. We piloted it here and continue to do so at our Learning Lab in our LIFT facility. We're hoping to have our students back full-time here soon. But it is a 3-year curriculum that is foundational for the next generation of multi-skilled technicians that are so desperately needed in the manufacturing sector. So you can see on the screen here, year one focuses on material science, then gets into advanced manufacturing. That is taught at our Learning Lab. You can see all the various labs that we have here, and you see we do offer skilled trades certification that is the next step up for more adult learners, folks that are ready to enter the workforce right now today, with jobs that are available right now and today. We offer certification programs in CNC, welding, robotics, industrial technology maintenance. CNC, welding, industrial technology maintenance are the most in-demand jobs. Robotics is the fastest growing, and that is why we offer industry-recognized, nationally portable credentials for those students. And those same majors are available in our Operation Next program, this program we're most proud of. It is a program that was designed initially for separating men and women from the military right before they leave the service. They complete their active duty 6 months prior to their separation date. We offered them the opportunity to earn a credential in one of these in-demand jobs so they can begin their next career, begin their civilian career immediately. So that program began as a pilot back in Fort Campbell, Kentucky in 2018. It has since grown to service the National Guard and Reserve members and their spouses, critically important, their spouses, here in Michigan, in Wisconsin, in Florida. We also are working in the Hampton Roads region of Virginia for those separating men and women from the military. So we are very proud of that program, to have that program at Lift. So I mentioned we are a membership organization. We're a nonprofit public-private partnership between industry, academia, and government. So what do you get from being a member? Well, you get all of the things you see on the screen here. From being a trusted advisor, we're going to give you the best advice possible. We're not here to sell a particular product or service. We just want to gather the brightest and best minds from around the country to help you move into the smarter manufacturing future. We are a technology accelerator looking to move those good ideas from idea over the valley of death into commercialization. We're not commercializing things, but we help put the teams together and enable folks to do just that. We're a technology showcase. We invite you to come visit our facility in Detroit when you can do so. If you're ever in town, please give us a call, give us a ring. We would love to show you around. We are a connector and convener. That's why we're all here today. So thank you very much for joining us. A talent developer, I already spoke on that. How we're trying to prepare the students for the workforce of tomorrow as well as today. And finally, we are a government partner. It can be unruly, unwieldy, particularly for small and medium-sized organizations to work with the federal government. So we are a conduit to do just that. So thank you very much for giving me some time to speak about Lift. I encourage you to follow us on our social channels or reach out to us on the phone or via email or on our website. We'd be happy to answer any questions. So in the meantime, that's enough about Lift. I'm going to turn it over to Nick Estock from AddUp to share some information about his work and his team's work with additive manufacturing as it relates to defense. So Nick, the program is yours.
All right, thank you, Joe. You just let me know that's coming through, okay?
Yep, I can see it just fine. Thank you.
Perfect. All right. So thank you again. Appreciate everybody's time for logging on and being here. So my name is Nick Estock. I'm the product manager for North America for both our powder bed fusion and our DED lines, both our technologies here in the US. So just a quick agenda of what we want to cover with you guys today. So we'll just do a quick company overview, kind of the background of the company, how we got started. We want to review traditional manufacturing versus AM. Why would you want to use additive manufacturing? We'll share with you both the modalities that we have in-house, our powder bed fusion and direct energy deposition, and the differences, why you would choose one versus the other, and which applications best suit each of those two technologies. And then how this is being used in the defense industry. And so then we'll wrap up just on how we can help any of you or any customer from powder to parts. So how you can solicit our services to help you through your adoption cycle of additive manufacturing. So it's just a brief background on the company. So AddUp's actually a joint venture between Michelin and Fives. So for those of you that don't know, Michelin's been using additive manufacturing since the early 2000s to create their tire sipes. And so they've really become the power user of this technology. As their abilities and understanding of the technology grew, they were actually pushing the limits of what the machines that were currently on the market could actually do for them. and they decided to create their own. So they took this power user, this expertise with the technology, and solicited the help of Fives, someone who has 200 years in manufacturing experience in machine tools and automation, to create AddUp. So Michelin, again, being the powder user, and Fives being the industrial manufacturer of industrial equipment. So like I said, Michelin's been using this technology since the early 2000s. They originally did this actually to truncate or shorten the development cycle of their tire molds. So they took a typical development time from 9 weeks down to 2 weeks. As they continue to do this, they were able to achieve more complex geometries in their tire sites, and actually then eventually move the technology into production. And today they actually produce over 1 million of these tire sites every year in a 24/7 lights out production environment, both in France and here in the US. So again, Michelin and Fives decided to launch AddUp in 2016. We were born. We actually acquired Beam, which is our DED technology, in 2018, and have subsequently also acquired Polyshape, which is a service bureau in both France and Italy, in 2019. So this really gives us the complete capabilities to service our customers, not only in 2 technologies, but throughout the entire life cycle of a product, helping them from design, identification, business case, design of that part, and all the way through the manufacturing process as well. Okay, so why should you use additive manufacturing? Where's the value? What's the point of doing this versus traditional manufacturing? So there's unique or inherent challenges in traditional manufacturing, such as your lead times, the internal features. You can only actually, if you're doing this subtractively, right? So traditional manufacturing is typically a subtractive process. You can't have internal features or conformal cooling. When you're doing the subtractive process, you're wasting a lot of material. So you have a high scrap rate of material that you're removing from your base part. It limits the amount of design freedom you have. So young engineers, as they're learning how to design new applications, they have to do that for a manufacturing process, and so they're limited in the geometries that they can create, because they know the tool maker or the robot needs to be able to actually achieve that geometry. Another benefit of additive manufacturing that is a challenge in traditional manufacturing is multiple materials or gradients of materials, adding additional parts or additional complex features onto existing parts, or long lead times that we kind of talked about before. So prototyping or short run production cycles, you have to pay for this tooling up front that can be very expensive and a significant amount of lead time. So additive manufacturing solves a lot of these challenges that can be better utilized, not only on the prototyping phase, but also in your production phases. So where's the value in additive manufacturing? Additive manufacturing is not a cheap manufacturing process by any means. So you have to really identify areas in which you can extract the value of this expensive process to make your business case real. So one way to do that, right, and certainly would be very important for aerospace type customers, right, is reducing the overall mass of the object. So either via topology optimization or part consolidation, you can reduce the total mass of a part because you're actually starting with nothing and only adding material where you actually need it. And in applications in which motorsports or aerospace, where weight is of utmost importance, that can be a real powerful value generation mechanism. Reduce labor costs. So all of that machining, all of that time to go build out that part can be reduced, because you're actually going to print only your end or near net shape part. New materials or new properties. Adding additional functions inside of an existing volume. So not just part consolidation, but function consolidation. Can you actually take this bar that's simply a strut and add heat exchanging elements to that same application? Thermal management is very powerful in additive manufacturing because we can create these complex internal channels, conformal cooling channels. Thermal management is a great application for additive manufacturing, as you can really optimize the cooling circuit to best suit your manufacturing process, whether that's heat exchangers, cold plates, or even tooling. New shapes, new geometries. So again, opening up that design freedom that you would not otherwise have in traditional manufacturing. And mass customization. So we can take a digital file and make an individualized, in this visualization, an individualized implant on a mass customized basis, because you only have to make a digital file for each one of those rather than a tool for each one of those. And so therefore it leads you to the second one, or the next one, which is you can produce these parts without tooling, right? Which is going to reduce your lead times down significantly, cut down a lot of your NRE cycles as well. Again, so reduce time for industrialization. And so for really expensive alloys, you're actually wasting a lot less material. So think about your titaniums or your Inconels, exotic materials that are really expensive, or even in the jewelry sector. You're going to cut down on the amount of raw material waste. And then lastly, worn and repair objects. So if you have an existing tooling that is starting to wear, rather than scrapping that and have to replace it, additive manufacturing via our DED technology can actually go back and rebuild those areas that you had lost. Excuse me, there's one more, and also just simply producing complex geometries that you would otherwise not be able to achieve with any other manufacturing process. So let's look a little bit at the differences between the two technologies. So powder bed fusion, shown here in purple, is excellent and very proficient at obviously complex geometries, rapid prototyping, short and large volume production runs, very strong material qualities that are coming out of this technology. Where it lacks, and where DED actually shines, and why they think these two technologies really complement one another so well, is in speed of construction, size of parts, feature addition, multiple materials or gradients of multiple materials, and component repair. So also adding materials to an existing substrate would not be possible in powder bed fusion, but is possible in our DED technology. So I'd like to share with you a little bit about our machine and our powder bed fusion technologies. So the FormUp 350 is our powder bed fusion machine. It's got a build volume of 350 cubed. It's modular. It can actually have anywhere from 1, 2, or 4 lasers. This can be field upgradable after the fact. So you can actually start with a 1 laser system and upgrade that system rather than having to buy a whole new one at a later date. So this machine is designed and intended to ramp up with your production schedule. It can be configured with a roller, blade, or a brush recoating mechanism. So we are the only machine OEM that offers a roller system. And the reason we do this is we actually utilize a fine powder. So a PSD, a particle size distribution between 5 and 25 microns. And the roller allows us to spread that effectively across the build. We're going to talk a little bit here in a few slides later on why we use this fine powder and what it allows us to achieve. And then we have a full suite of materials that you can see here. Maraging steel is the original one that Michelin uses for their tire types, and we've expanded further beyond that, as you can see. So this machine was really built on 4 pillars. When Michelin and Fives set out the joint venture, they set out the machine design against these 4 pillars, which are productivity, quality, flexibility, and safety. So I won't get into every single one of these, but just to pick out a few. The productivity, the reason why we use this fine powder PSD is it allows us to build really low overhangs, has a really good surface finish, which is reducing the amount of support structures and post-processing needs for your end application, just increasing your productivity. Again, quality, I already mentioned the surface finish. We also use a 3-axis system that I'll talk about here in a moment. It gives us really good control and stability over our laser position and profile, shape of that profile. Flexibility. So I already talked about a little bit having 1, 2, or 4 lasers. It's field upgradable. You also have flexibility in your recoating method, whether it's a roller or a blade. And it's a totally open platform. So as we provide our customers parameter sets for any given material that they choose to load on the machine, all of that information is completely open to them. They can dial in or optimize any of those parameter sets to specifically meet the end use needs that they might have. And lastly, and probably most importantly, is safety. So we have we'll talk about our autonomous powder module probably in a little bit. It's a closed loop, fully inerted system that completely isolates the operator from having to load or unload powder or being exposed to that powder during that load and unload process. So this is really intended to minimize the contact time that our operators have to interface with that powder. So our system comes with a bidirectional recoating system. So hopefully you can see this video that's playing here in the upper right corner. We have these 2 small trays that will dose in front of the recoater from either side. That allows us to recoat. You can see the recoater can stay in a home position on the left or the right side. That actually increases our productivity. So you're not waiting for the recoater to return to home for each one of these cycles. So we just have an example here for a normal 36-hour build or what would require 23 hours of laser on time. If you had a monodirectional recoater, you would spend 13 hours recoating in the recoating mode. With a bidirectional system, that's reduced down to 8 hours. So in total, that's actually about a 14% total increase in productivity just by being able to recoat from both sides. So I mentioned before, we have a 3-axis scanner, and this differs from an F-theta lens control that you might see on other equipment. What this allows us to do is actually we focus the beam actually in front of our galvanometers, and that allows us to maintain this spot size anywhere on the build plate. So you see on the left here, we still maintain a relatively round shape of our beam. As you get out into the edges with an F-theta lens, you actually get this elliptical shape that you can see here on the right. What this really means is that you get less control of what you're printing. So the geometry and the tolerance in which you're controlling starts to degrade as you get further and further away from the build plate or the center of the build plate. Our system allows us to maintain control and shape of our laser anywhere on that 350 build platform. Additionally, all 4 of those lasers can reach the entire build platform. So you're not quarantined or sectioned into a quadrant with an individual laser. So what does all this mean? It means increased design freedom for our users. So rather than being constrained, even in traditional manufacturing we talked about earlier has design constraints. Well, additive manufacturing also has design constraints, even if they are greater than traditional manufacturing. And so our system pushes that envelope just a little bit further. So rather than having to build at 45-degree angles without support structures, we can actually get down to 10-degree angles without support structures. It allows us to create very large pass-throughs or hole diameters up to 40 millimeters. We can get really fine feature resolution, 0.2 millimeter thick walls. So this is great for internal geometries or internal channels where you need really a fine feature resolution. So another added benefit, and again, another feature that was important to Michelin as they designed this system was to be able to achieve fine feature resolution, but also a really good surface finish. It was very critical for their application. So this roller and fine powder combination allows us to pack our build bed a little bit better, which allows us obviously to print without as many support structures, but also gives us a much finer or a much better resolution on our surface finish. So showing here both in Inconel and in Ti64 for a given upskin and downskin. And what I mean by upskin and downskin is The surface as it relates to horizontal. So the bottom surface would be what we call a down skin, and the angle is the relation to it from horizontal. So 90 is a vertical surface. So for any given orientation of your geometry, we can actually improve your surface finish with this combination of roller and fine powder by about 10 RA for both shown here in Inconel and Ty64. And just further demonstrating that here, so showing the very significant overhang and shallow angle of 15 degrees, we can actually achieve surface finishes still down at 22 microns. And for that vertical surface, we can get as smooth as 6.3 RA microns. And so I think I mentioned earlier, we have an autonomous powder module. So what this does is this handles all of your powder management for the system. So the system, as it's being supplied powder, comes through this hopper. It's being put on those racks, as you saw in that bidirectional recoder little video. The recoder is pushing that powder across that build plate. You always put enough powder. You actually put extra powder on that rack to make sure that you push it across the entire build plate, and you actually have some excess, and that gets pushed over to the other side. That's collected. It's actually being recycled, put back in this hopper. It's being re-sieved, re-dried, and added back to your build chamber. So this is managing all of your powder management is taking place inside your powder module here in an inerted environment, fully controlled. And as I mentioned earlier on the safety element, so we actually have our inerted glove box. So this actually has a side door. You load your powder containers into that door. You actually inert this glove box completely down before you open those containers. So again, your operators are not being exposed to this loose powder. You can pour that then into the hopper that's a part of the glove box that will actually automatically route over to the autonomous powder module. So again, keeping your operators out of harm's way and not unexposed to the powder. When you're ready to empty the autonomous powder module, you can actually reverse the functionality. So you can put your empty containers back in here, put them underneath a nozzle, and we'll actually unload the powder out of your autonomous powder module back into your container in the glove box for removal and safe storage. We have two different gas flows across our build platform. So there's one that goes across the build plate itself, and this is integrally important. As you're melting powder with your laser, you're actually kicking up and creating soot and other carbons, and you want these to be pulled quickly out of the way in a laminar fashion, as to not interfere with your laser as it's trying to print the next section of geometries. So having a consistent, smooth airflow to pull away that contaminant is very critical to your part quality. We also have a secondary gas flow over top the lens in which the laser passes through. Again, this is critically important, as if that gets dirty, that will also interfere with your laser. So making sure that stays clean throughout the duration of your build with a clean, smooth laminar gas flow over top of those lenses. And we also have a hurting filtration module as a part of our system. And so this actually helps us maintain a laminar gas flow over the entire life of the filters that we talked about just a moment ago. So this system actually doses with calcium carbonate, shown here in blue in this video. That's actually going to passivate and capture any residue or soot that's coming through that gas flow. And will actually drop into that container. So that minimizes the amount of particulate that builds up onto your filters, which extends your filter life. Additionally, we have a reverse pulsing or unclogging cycle that runs after every build that will actually pulse the backside of your filter and knock loose any particulate matter that did make it over to your filter. So this actually increases your filter life up to 3 years, which obviously, again, means more productivity and less downtime for our end users. So to touch on software here just quickly, we do offer a full suite of software packages for our customers. So we have our own CAM package, or AddUp manager, which is our build prep. So this is where you do all of your laser assignments, your scan strategies, your build layout. Embedded in that is a distortion simulation add-on. So this actually is embedded into the system. You can actually run a simulation of your print. It will highlight to you any high stress areas, any potential areas where you might have a recoder interaction, any areas of significant distortion, and you can actually output a compensated file from that that you can send straight to the printer. This is really nice because you don't have to import and export this compensated file to and from multiple software programs. It can be done directly within AddUp Manager and sent directly over to the machine. Encore is our user interface on the machine. And dashboards is a in-process monitoring software that is monitoring over 80 key process parameters that are taking place in the machine, from oxygen levels, temperatures, air flows, laser power, giving you complete visibility to what's going on during the build. If you already have your own CAM package that you prefer, we actually have the ability to create a plugin for any of the common standard CAD packages. So our system is interoperable with those via our N-Twin package. We actually are expanding our AddUp monitoring solutions later this year with both our recoat monitoring and our melt pool monitoring. Okay, so let's switch gears a little bit to our DED technology, our direct energy deposition. So DED, the simplest way to think about this is it's really a 5-axis CNC machine. So it's actually using the same G code you would generate for any other CNC equipment. The main difference is, instead of having a tool at the end of it, we have a print head at the end of it. So our machine is able to fully inert down so that you can use reactive materials. And powder is actually being deposited through this print head. I'll show you here another slide in just a moment. It's being deposited exactly where you want it through this print head, and the laser is coming through coaxially to generate your melt pool. So some applications for DED would be repair. I think I touched on it before. Feature edition and near net shapes. We'll kind of walk through each one of these in some examples. So repair is a great application. So in this example, we're showing a shaft seal. It has knife seals at the end of it, and these tend to wear out over time. This part's made out of titanium, so it's a very expensive part to machine from scratch. We can actually go back in and add these knife seals, these worn knife seals, back onto the part. And then there's just a small machining operation to get them back into tolerance. So rather than scrapping this part, you can actually repair this part up to 4 times before it has to be scrapped, extending the life of the part pretty significantly. Turbine blades, tips on these turbine blades wear out. So adding material back to that turbine blade allows for, again, extending that life of that part. Feature edition. So if you have either multiple alloys or a really expensive base alloy that you don't want to machine down and have significant amount of material waste, you can take a standard extruded base component and actually add your features to that. So this is, again, a great opportunity to add your features only where you need it on existing substrates. So you can obviously use then compatible alloys to put exactly the material you need and the alloy you need in the exact location that you need. And actually, so this is a great example of hybrid technology. So this is actually using our powder bed fusion for the base of this piston skirt. So we're able to put this intricate lattice that not only reduces your weight, but actually increases wicking of your oil transport. But it's done in a cheaper, more cost-effective alloy in Merging 300. And then you can add via our DED process your high temperature nickel-based alloy to that top piston head that's going to see the higher temperatures of the combustion engine. So multiple alloys, multiple modalities, multiple functions being achieved here. So lastly, near net shapes. So rocket nozzles, engine casings, iso grids are all great applications of our DED technologies. You can create these very large geometries that you would not be able to otherwise achieve, certainly via powder bed fusion, or even a traditional manufacturing would be entirely way too complicated to create. DED is, again, this 5-axis machine, but you're only adding material instead of subtracting it exactly where you need it. So just to touch on our nozzles just a little bit further. So we actually have two sizes of print heads, our 10VX and our 24VX. So they just essentially have a different nozzle at the end of it that allows us to make different size weld beads, different size melt pools. So our 10VX, we can achieve about a 1 millimeter thick wall or a thin wall. And our 24VX is about a 2 millimeter thick wall. So you can increase or decrease your production rates or your feature resolution by selecting which head you need for your specific application. Unique to our nozzles is this dual coaxial gas flow. So there's one gas flow that's actually carrying, so it's argon and your powder. It's actually carrying the powder through one coax. We actually have a secondary shielding gas or shaping gas that allows us to create this longer jet that desensitizes our process to the focal point. So if you look at this top left picture of a single gas flow nozzle, you kind of see this hourglass shape. That means your substrate has to be right at that fine focal point of that hourglass to make sure that you're controlling your melt pool. Our system with a shaping gas, we actually desensitize the process so that we can actually elongate that focal point so that if there's a misalignment due to thermal growths or tolerance builds up or distortion, if that is to occur, our system is less sensitive to missing our substrate with this elongated focal point. So we have two types of, or two sizes of DED machines, our Modulo 400 and our Magic 800. Again, they're essentially the same equipment, just larger build envelopes and higher payloads for obviously the larger machine. So 600 by 400 by 400 for the Modulo 400 and 1200 by 800 by 800 for the Magic 800. So let's look at a few different use cases for AM in the defense industry. So this is a good example of feature addition, rapid prototyping, among other things, and actually getting better performance out of this process. So here's a door skin for an armored vehicle. These are typically welded on with a normal MIG weld. With our process, we were actually able to create some of these feature additions. One, we could do it faster because we don't require any tooling or fixturing. Two, we were able to do it without creating a heat affected zone or as substantial of a heat affected zone in the armor, because we're actually putting in less energy into the process. Rocket nozzles are another great application. So as we continue to invest money in hypersonics, you're going to see more and more of this. So this is a rocket nozzle with integrated cooling channels. So this is actually done. We don't normally think of cooling channels or internal channels with our DED process, but with our 10VX head and that fine feature resolution, we're able to get out of it just a 1 millimeter thick wall. We're actually able to generate this geometry here with internal channels that run circumferentially around this rocket nozzle. And here's just showing you a video of the path as we print that rocket nozzle. So you can see the nozzle always points directly down because this is being gravity fed, or the gas is carrying the powder, but is then being gravity fed down the print head. It is always in that vertical orientation, and so we use our 5-axis trunnion and turntable to accommodate the printing operation. Lastly, here we offer our what we call our FlexCare system. So this is a turnkey system that's actually integrated into a shipping container. And this is intended and designed to be modular, so it can actually scale as the needs will require. So this can be delivered in theater or near theater. This is specifically designed to handle all of the ancillary equipment needed for our machines. So it has your sieve stations, your vacuum stations, depowdering. Everything can be contained in this single modular shipping container and can be transported and delivered directly where it's needed. So lastly, we'll talk about the one-stop shop, that is AddUp Inc. So we touched on quite a bit of this already, but again, we have powder bed fusion and DED technologies in-house. So we actually have two DED machines in our facility in Cincinnati, one of the 400s and one of the 800s. We actually have 6 powder bed fusion machines at our Cincinnati facility. We offer a full suite of training programs via our AddUp Academy, and we also offer consulting services out of our Cincinnati facility. So if you guys have parts that you're interested in, we can help evaluate that with our application engineers to really understand if this makes sense for additive, both from a design and functionality level as well as a business case perspective. We can prove it out for you. So we can help you with the design. We can help you with the materials and process and generate proof of concept parts for your team for further evaluation. And then lastly, of course, being an OEM, we can help you scale. So we offer machines for both modalities. We offer workshops that can help you identify parts and business cases that make sense, as well as full customer support thereafter once you're in production. So as I mentioned before, our Cincinnati facility, actually our global operations, we are a French-based company. So our headquarters is in France, but we have our North American entity in Cincinnati, AddUp Inc. Again, with the 2 DED machines and 6 powder bed fusion machines. We are recently ITAR certified, and will be AS 9100 certified here in the coming weeks, actually. So we also have full capabilities across the globe. So in our European offices, we have over 40 different machines, from a powder bed fusion to powder-based DED, as well as a wire-based DED even. As I mentioned, we acquired Polyshape back in 2019. So we actually have full end-to-end capabilities from designing of the part, but full production of the part and post-processing of the part through our partners there as well. And that is it. So perfect. I think I left exactly 15 minutes.
Great job. Yeah, you timed that exactly right. I love it when a plan comes together, as they say. So, hey, thank you so much for the presentation. Thank you for the information today. A couple of questions have come in. I know we have a little bit of time. Again, if you do have questions, please use the Q&A function on the Zoom toolbar, and we'll do our best to ask as many of them as we can. I'm glad you mentioned the ITAR certification that you have. That is important to us. It's important to our friends at the Department of Defense. Can you talk a little bit about just that capability you have and the ability you have to work on DoD materials and DoD work with that certification?
Yeah, thank you. So we've fully firewalled off our digital systems. So our servers, our entire entity in AddUp Inc. is firewalled from our parent company in France. And so with all the correct protocols in place, we're able to achieve our ITAR certification end of last year. So we're fully equipped and capable to handle any work with our DoD partners. Good.
Well, thank you. I wanted to make that clear. So a question I ask a lot of folks that are involved in additive is, at Lift, as I mentioned, we're involved in a lot of different materials, a lot of different processes, whether it be extrusion or stamping or forging or and additive and subtractive, other kinds of work. So but additive has this feel where it's the, you know, it's the sexy thing, right? It's people want to get involved in it. People may think it's a solution to everything. But if I have a part that I think could be manufacturing additively, what kind of process, where do I need to start? What kind of process do I need to go through to really figure out if that's the best method, or maybe it's not the best method? What kind of process do I need to go through for that?
Yeah, so it's really in my mind always about building out a business case, right? So understanding what that part would cost in the supply chain impacts associated with building that traditionally versus additively, right? So understanding the inputs not just from the machine cost, but from the post processing cost on the additive side, but understanding what your tooling cost and what your inventory and your work in progress would look like on the traditional side. These are all the inputs and the many layers to an onion to understanding your full business case. So it's much more than just understanding, did I design this part for additive and can it be printable? To make it make sense to actually go through with that in the production environment. As many layers of an onion
Right.
to fully understand your full business case.
And do you guys then go through and you just talk about the inputs? Do you guys then study the outputs to make sure? Because we talked about before the materials, process, and systems to make sure that whatever piece we're making, whatever part we're manufacturing, is able to act in a way and behave in a way it's supposed to in the system it's going to end up in. So do you guys study the end material that you guys have to make sure that it is capable?
Yeah, absolutely. So all of our machines go through a qualification process, right? We've fully characterized our materials that are coming off these machines to understand what that really looks like. And so as you go through your specific qualification of your application, you have this now data set to look back on to say, okay, is my current materials, my current application, is everything that's going on in the machine still buying into what I know to be good and valid materials and parameters that we've established at the beginning of that production cycle.
Right. Awesome. Okay. So a couple questions from the audience here. Do you vary spot size during scanning to induce variations in grain size or boundary or shape, and as a way to improve material strength or fatigue properties as you're going about the scanning work?
That is an excellent question. So the short answer is yes, we have that capability to do that. The unique thing about additive manufacturing is it has this inherent ability to continue and always optimize. So you can always further optimize and further optimize and further optimize. So it really just comes back down to that business case, right? So does your application need something different? Are you trying to achieve something very specific? Certainly you can go develop that parameter set of that capability. The functionality exists within the machine. It's within the technology. It's there, but identifying what level of investment you're going to need in order to get the desired outcome is the trade-off that you're going to look at there.
All right, talking about investment, how large do you envision the DED machines getting in order to build very large near net shaped components?
Yeah, so from a technology standpoint, there are folks out there that are making fuselages to rockets that are meters, right? 35 feet wide and 60 feet tall. For our specific modality or our blend or our flavor of DED, the Magic 800 is probably not going to get too much bigger than that. I mean, it's already building a pretty large envelope, but when you're thinking of powder DED as opposed to a wire-based DED process, it's going to be a smaller scale relative to the wire-based technology.
Is there an application or example where you have where powder bed fusion and DED could be used together?
Yeah, so actually I showed a couple examples. We talked about only one of them with a hybrid piston, but we actually had another example. I didn't dive into it. That isogrid that you saw on the near net shape, we can actually print the casing itself in powder bed fusion and then go back and add the isogrid to the part with our DED technology.
All right. Have you guys looked at scandium aluminum alloys for your additive machines at all?
That is not currently on our roadmap, no.
Got it. Okay. Can you selectively feed different powders simultaneously if I want to produce parts with controllable alloy gradient from base to surface, how do you suggest doing something like that?
Yeah, so our DED technology, you can actually put up to 4, maybe 5 hoppers on the machine at once. So each one of those can be same alloy or different alloys. And so you can actually create a gradient or a blend and transition from one base alloy to the other base alloy over a period. I don't know that we've actually tried to intentionally print 2 out of 2 hoppers simultaneously for an extended period of time in order to achieve a certain material matrix, but I don't see any reason why you couldn't do that.
I encourage folks to reach out to Nick and his team. Speaking of which, do you have what's the best way to reach out to you after this webinar?
Yeah, so if you're going to send out some information to the attendees here, I can give you my email address, but it's nick.estock@addupsolutions.com. We can make sure to include that with any documentation we send along.
Yeah, we'll make sure to have folks have that information right at hand when we follow up. Can we expect a truly isotropic material in the printed part?
It is a layer by layer process. So we use, to get isotropic materials, we use a heat treatment cycle after the fact.
All right. I think we have time for 1 or 2 more. So don't be shy if you have some questions. Can you use the roller system with any type of metal powder on the AddUp machine, or is it material specific?
Nope, it's across any of our alloys. So anytime we develop a new alloy, we always make sure that we're doing it with our roller system and our blade system to make sure there's multiple configurations that are validated. All
right. Well, listen, hey, I appreciate you taking the time to work with us today and present to us today. Appreciate your membership. Lift, any folks out there interested in membership, certainly give us a jingle. We'll be happy to talk with you about that as well. So thanks for taking time to join us today. I think if you do have questions, reach out to Nick at AddUp directly. You can reach us at Lift. We'll be happy to make that connection as well. You can, again, follow us on our social channels, call us like olden times, send us an email or visit us on the website. We'd be happy to do that and give you any information you'd like about AddUp or anything else we've got going on at Lift. So Nick, thank you again for the presentation. Thank everyone for joining today. Give you back a few minutes left, a few minutes of your day back, and then stay tuned for our next webinar. Stay tuned for your emails, and hopefully you'll register, and we'll see you. We'll see you all soon. Thanks, Nick.
Thanks, Joe. Appreciate everybody. Thanks.
Yep, we'll see you.